To illustrate how the Schrodinger's equation works, we're going to look at what's known as particle in a one-dimensional box, okay? So in this scenario, we have one electron inside of a one-dimensional box, so there's only one axis. In this case, we're going to call it the x-axis, okay? And it is between the x distances of 0 and a, just any number a, okay? So we can alter the size of the box, in other words, from 0 to, if we want to make a equal to 1 angstrom, or we can make it 1 meter. We can do that, okay? In this case, a is just representing, right, how much distance there is between one side of the box and the starting point of the box, okay? And again, it's just one dimension, okay? Now, we're going to put one electron in here. Okay, the stipulation being that the electron can be somewhere within this box, and we're going to find a wave function that describes how the electron is distributed within the box, okay? Or rather, again, which gives us information it will give us, the wave function will give us ultimately information, the probability of finding that electron within the box. Now, there are boundary conditions, okay, and this is set by making the at distance 0 and at distance a, we have a potential of infinity, okay? So that means the electron is inside the box, and the potential energy at the 0 point and at point A are infinity, and therefore the electron cannot escape this box, okay? It is trapped inside this box. And so, again, the goal is to find a wave function that describes the probability of finding that electron anywhere within the box between 0 and A, okay? Importantly, right, the potential anywhere else that's not at the boundaries, right, the potential is 0, anywhere in between x equals 0 and x equals A, okay? And so for solving for a wave function that will satisfy the Schrodinger's equation, we'll find that there are actually several solutions to this, okay? And so we can generalize what the solution is, right? Where we say the wave function in this case, I won't go through the math for solving this, but the wave function, the function for the wave function is the square root of 2 over a times sine times n times pi over a times x, okay? So the function in terms of the distance of the position x within the box, right, is equal to the square root of 2 over a. This is a normalization factor, okay? So remember that wave functions need to be normalized, and so if we do the wave function times the conjugate of the wave function and integrate that overall space, we need this to be normalized, so it all needs to be equal to 1. Okay, this is the normalization factor that allows for that condition, okay? Multiply that by sine of n times pi over a, so a, right, is the same value a, right, how large the box is. So what's telling you is that, as we'll talk about in a second, the period, right, of the wave function is dependent on the size of the box, right? N, right, this is going to end up being our principal quantum number, okay? But what it's saying in this case, right, just generally, is that n is any integer value. So 1, 2, 3, 4, etc. Okay? So, like I said before, right, there are several solutions that would several wave function solutions that would satisfy the Schrodinger's equation, and so the way that's generalized by these different ones are all different based on what the value of n is, okay? And so this is the wave function that allows for solving for the particle in the box. And then we can use, right, we can apply the Hamiltonian operator to the wave function, and we can solve for energy, okay, for the wave function that we're using, okay? Now, keep in mind, right, Hamiltonian simplifies because the wave function is inside the box, and like we said, the potential within the box is going to be equal to 0. So we don't have to think of that. So we only apply, right, we have the Hamiltonian becomes this term, which is a set of constants, which is Planck's constant squared divided by 8 times pi squared times the mass of the electron, okay? And so really what we're doing is we're applying, right, the differential, the d squared dx squared to the wave function. And if we do that, what we find in the end is that the energy for the wave function is going to be equal to h squared times n squared over 8 times m times a squared. So again, these same terms are up again. We have Planck's constant. We have n, which again is an integer value corresponding to the same integer value that was used to for this wave function, okay? The mass of the electron, and then the size of the box, all right? And from there, right, we can then correlate the energy to the, we can correlate the energy to the wave function.